In this lecture, we'll talk about how hydroelectricity is generated, where it is generated, and where there is potential for future hydropower development. We'll also talk about how hydropower projects can change the hydrology and ecosystems of rivers, and some of the other drawbacks associated with the use of hydropower. Here we are looking at a photo of Cougar Reservoir in Oregon. This reservoir is formed by a dam that is used for both flood control and hydropower production. This photo, from a few years prior, gives you a sense of what a reservoir looks like when it is nearly empty. Before the 519-foot-high dam was built in 1963, forests would have extended down to the valley bottom, which the river would have occupied only a small part of. Now the reservoir in this valley helps generate electricity for about 3,500 homes, in addition to providing flood protection for the downstream communities. Let's go over the basics of hydropower. To start with, it's the largest source of renewable energy on a global basis, and it is a form of energy used to generate electricity. Until recently, it was the largest U.S. source of renewable energy as well, with 22% of the renewable portfolio in 2019. Unlike fossil fuels and bioenergy sources, hydroelectricity is not carbon-based, and after the initial construction of the dam and reservoir, it is generally considered to generate carbon-free electricity. Hydroelectricity can produce up to 84 times the energy required for its production and distribution. In other words, it has an EROI of up to 84, although it's likely that most of the best spots for hydroelectricity generation have already been taken, at least on some continents. Dams can also serve multiple purposes, just like I showed you in the first slide. For example, dams built for flood control can also generate hydroelectricity and provide opportunities for recreation. There are some drawbacks, however, to hydroelectricity, and we'll discuss them. But first, let's talk about how it actually works. A dam is a wall in a river that holds back water into a lake or pool known as a reservoir. The more water flowing past the turbine, and the higher the water at the top of the reservoir is relative to the elevation of the turbine, the more energy that can be produced. Water flows from the reservoir through a tunnel called the penstock towards the turbine where electricity is generated. At the top of the penstock, there are gates that control how much water can flow through the penstock at any given time based on the electricity demand and reservoir conditions. As water flows past the turbine, it spins the blades and rotates the shaft to which they are attached, generating electricity. The electricity generated is then transmitted through the electrical grid to where it is demanded. Water leaves the penstock and enters the river below. Just as a side note, this process of spinning turbine blades to rotate a generator shaft and produce electricity is common to most forms of electricity generation, including fossil fuels and nuclear. Often it's steam that's used to turn the turbine, but in hydropower, it's liquid water. On the previous slide, I showed you a classic impoundment reservoir where the dam is built into the river valley and water flows through the penstock and directly back into the river. There are two other types of hydroelectric dams worth knowing about. One is a diversion dam, like the system shown here. In a diversion dam, water is diverted through a pipe or canal to the turbine. In this hydroelectric scheme in the Oregon Cascades, water flowing in the Mackenzie River is impounded in the Carmen Diversion Reservoir in the upper left part of the image. Water doesn't usually flow over or through the dam. Instead, the flow of the river is diverted through a tunnel to the Smith River Reservoir. From there, water from the Mackenzie River and the Smith River are both diverted through a tunnel to the Carmen Power Plant, where electricity is generated and the water is released back into the Mackenzie River Valley. But the water immediately flows into Trailbridge Reservoir, which is formed by an impoundment dam, and even more electricity is generated before the water begins to freely flow down the Mackenzie again. This system of diversion and impoundment dams allows the utility to take advantage of larger river flows and large elevation changes without having to build giant dams. It powers about 16,000 homes in Eugene, Oregon. The downstreammost reservoir also helps mitigate some of the changes to daily river flow that can result from hydroelectric production. More about that in a few minutes. The final type of hydroelectric dam is one designed for pumped storage. In this system, water is pumped up into an elevated reservoir, like shown on the left, and then allowed to fall to produce electricity. Surplus electricity at night, when demand is low, is used to pump water into the reservoir. One such system is shown here from the state of Missouri. The pumped storage reservoir, shown on the left, is located at the top of the mountain here. Water flows through a penstock, this yellow line, from the upper reservoir to the power station when electricity needs to be generated. Then, when demand is lower, water is pumped back up to the upper reservoir from the lower one, shown at the bottom of the image. In pumped storage systems such as this one, because electricity is needed to pump water back up into the upper reservoir, it's never actually a net producer of electricity. Instead, such systems are net consumers of electricity. However, they can serve an important role in providing extra electrical generating capacity when demand is high, such as on hot days when the people in Missouri are running lots of air conditioners. So these systems are more like batteries than generators. Also, careful engineering of all reservoirs, including pumped storage reservoirs such as this one, is necessary to keep the surrounding area safe from catastrophic dam failure flooding. If you look at the upper portion of the right-hand image, you can see a brown eroded pathway down the mountain. That's where part of the upper reservoir failed in 2005. Almost all hydroelectric capacity in the U.S. was built before the mid-1970s, and much of it is located at dams operated by federal agencies. Looking at the map, you'll see that most of the hydroelectricity generated is produced in states which have some steep topography. Mountains or canyons are helpful for hydroelectricity generation because they create narrow valleys where tall dams can be built. These tall, relatively narrow dams maximize the energy that can be generated while minimizing the width of dam and therefore the cost of construction and amount of land that must be flooded for the reservoir. Of course, water is the other necessary ingredient for hydroelectricity generation. But in the dry western U.S., mountains form sort of water towers where snow accumulates and feeds major rivers, making hydroelectric generation possible even in relatively arid regions. Note that there is less hydropower capacity in West Virginia and Virginia than you might expect based on their position along the Appalachian mountain chain. That may be because these states had abundant coal, so there was less pressure to develop other energy sources. Alaska also has relatively little hydropower compared to its topography and size, but that's because there is a low population to demand the electricity, and it's pretty isolated from the rest of the U.S. electrical grid. The era of building big dams is likely over in the U.S. because most of the good locations have already been developed and because environmental pressures have stopped major dam building since the 1970s. But that may not be true in other parts of the world. This map shows in blue the hydropower production as of 2004, while the red shows the potential production for each region. Notice that in North America, Europe, and Australia, most of the potential has been realized, i.e., there are dams producing hydroelectricity at most of the good locations. But in Africa, Asia, and South America, there is a lot of unrealized potential, and it is in these areas where large dams are now being proposed and constructed. These dams will produce more non-fossil fuel-based electricity for these regions, but there are always trade-offs. Now that we've talked about the types of hydroelectric facilities and where we find them, let's talk about the impacts of dams on river systems. We'll start with the example of Glen Canyon Dam, which forms Lake Powell on the Colorado River. It's the second largest reservoir in the U.S. and produces 5 billion kilowatt hours per year of electricity, serving 5.8 million customers. It's also just upstream of the Grand Canyon. and it's typical of the way hydroelectric dams can alter river flows, particularly in the western U.S., where spring snowmelt represents the principal water supply for the year. Before Glen Canyon Dam was closed and the reservoir started to fill in 1963, the Colorado River downstream had dramatic floods each spring and early summer, and very low flows in the late summer, fall, and winter. Once the dam was built, the spring snowmelt floods were used to fill the reservoir each spring, and there was a more even release of water throughout the year. The biggest flood that could be released from Glen Canyon Dam was determined by the capacity of the penstocks, so you can see how much smaller the floods were after 1963. We can zoom in and see what this looks like over the course of a typical year. The blue line represents the hydrograph before Glen Canyon Dam was built, and the green line represents the hydrograph after it was built. Note the very, very even flow throughout the year after the dam compared to before the dam, with a little bit of a bump up in the winter heating season and the summer air conditioning season. The post-dam green line also shows a daily sawtooth pattern because more electricity is used during the day than at night. As a consequence, more water is released from the reservoir during the day to generate electricity, and the river flow downstream is higher. At night, electricity demand is low, so water is held back in the reservoir and flow in the river decreases. What you can't see on these graphs is that the dam also releases water from the bottom of the reservoir, and that means it is much colder than the river temperatures were before the dam was built. Plus, the sediment being carried by the river upstream of the dam settles out in the reservoir, so the water downstream is quite clear, rather than the brown, sandy, and muddy water that the river would be naturally. This lack of floods, daily cycles in stream flow, and cold, clear water are all unnatural for the Grand Canyon ecosystem and for other western rivers. That brings us to the drawbacks of hydroelectricity as a renewable energy source. As we've already mentioned, dams require some topography, so they can't be built just anywhere. They also require permanently flooding some land, and that can displace people and wildlife. For example, the Three Gorges Dam in China required the relocation of more than 1.2 million people when it was built. Flooding the land can result in methane releases as vegetation decomposes at the bottom of the reservoir, and as more organic matter is washed into the reservoir over time. Methane is a powerful greenhouse gas, and this is particularly a problem in tropical areas. And that's where future large dams are most likely to be built. We've also already talked about how dams can change the streamflow patterns on annual, seasonal, and daily timescales in ways that harm ecosystems. I also already mentioned how they trap sediment. This can cause problems downstream, as the clear water can erode a lot of sediment from the riverbed and banks. Dams can also block fish movement. Some dams have tried to get around this problem by building things called fish ladders. But not all fish jump and are able to use fish ladders. And there's a height limit to dams with fish ladders. You can't build them hundreds of feet tall. And even with fish ladders, downstream movement of fish is still a problem. Dams also increase evaporation in arid desert areas, meaning that some of the water leaves the reservoirs and doesn't return to the river, decreasing total stream flow. Finally, in some regions, climate change is decreasing river flows, and thus the potential for hydroelectricity generation. For example, areas where glacier melt supplies stream flow, like the Cordillera Blanca of Peru, warming temperatures and changing precipitation patterns mean that the future of hydroelectricity is probably less than it is today. To summarize what we've learned, hydropower is a major global renewable energy source for generating electricity. The locations where hydroelectricity can be generated depend on topography and water availability. Hydropower can have a large energy return on investment because the energy inputs are in building the infrastructure. After that, the water cycle does the work. Generating hydroelectricity doesn't create air pollution like fossil fuel combustion does, but reservoirs may release methane, which is a greenhouse gas. Hydropower reservoirs can offer co-benefits for flood control, recreation, and other uses, but they have environmental costs for people and ecosystems that can be significant. Because many good sites have already been used and the environmental costs are high, new large hydropower projects may not be built in the US, Europe, or Australia. But in other parts of the world, more large dams are coming in the near future.